Hello everyone, and welcome to the Moving Right and Moving Left post activity. So this one's going to take a little while because we're going to really do two things here. First off, we're going to go over the summary page, right, of your activity, so you might want to get that page out so that you can compare your answers to mine. And then we're going to add in some things, and really it's just kind of giving some names and formalizing what we saw in the Moving Right and Moving Left activity. Whether you, depending on how you ended up doing this. So, first question, right? In every graph that you made, if you got rid of the schmutz on the outside before you let the car go and after you caught it, right? If you just watched it while it was moving, you always got nice linear graphs. And so what does that tell you about the motion of the car? Well, first off, remember that linear graphs have special kinds of slopes, right? They have constant slopes. And since it's a position time graph, we know that that means the speed is constant. So since we had a linear slope, therefore constant, we have a constant speed car, which of course we've determined when we did the toy car lab that that's the way the cars worked. Now, however, there were some differences in a couple of parts about those slopes. In, I believe, number 2, you did 3 different trials where you messed with the speed knob on the cart, and that resulted in different steepnesses of slopes. So what did you see that the steepness of the graph told you? Well, hopefully you said that it told you how fast the object was moving. The steeper the slope, the faster the motion. I think that probably makes a good amount of sense, right? Steeper slopes are moving faster. But then when you got to number 4, you saw something you might not have expected. This was the one where you had the cart and you made the car move back towards the motion detector to the left, right, in the picture. Move to the left. In 1, 2, and 3, it was moving to the right. In 4, it was moving to the left. And that manifested itself in a negative slope, right, instead of a positive. So hopefully you figured out that the sign of the slope told you the direction of the motion. Positive slopes generally mean you're moving to the right. Negative slopes mean you're moving to the left. And we can use words like right and left. We can use kind of math symbols like positive and negative. And by the way, if our one dimension is, say, up and down, it's what you assume. Up is positive, down is negative, right? Conventional coordinate system. Out of the board is positive, into the board is negative if you're doing 3 dimensions. Right? So each one of those can be indicated kind of with words or with symbols. And so notice here we're getting 2 pieces of information out of the slope of a position time graph. One tells you how fast it is by how steep it is, and the other gives you an idea of the direction it's moving by the sign. So that makes it a little different than speed. We're going to give a name to this after we finish up this summary page. So in number 3, you saw different y-intercepts in your position time graph. Why did it have different y-intercepts? Well, because those y-intercepts represented the starting position of your car. Starting position of the car. In some of the later ones, sometimes the y-intercept was above the time axis, and other times it was below the time axis. Since it represents the starting position, right, the answers to these questions have to do with where was the starting position. But you need to think about it like in the graph, it was where is that starting position in relation to 0. When you had a positive y-intercept, your car was always starting to the right of 0. Think about numbers 1, 2, 3, 4. Right? I think 5. No, sorry, 1, 2, 3, 4, and 6. Right? 1, 2, 3, 4, and 6, you all had positive y-intercepts because your car started to the right of 0. But in number 5, when we moved 0 into the middle of the track and started the car by the motion detector, now you got a negative y-intercept because you were starting to the left of 0. So hopefully by doing this activity, you saw how rich and how full of information a position time graph is. And it tells you a lot about the motion. It tells you how fast something's moving. It tells you what direction something's moving. It tells you where that motion is starting. Right? All of those things are things we can interpret from the graphs. Right? Now, the graphs are not the actual motion. Right? The graphs are just representations of the motion. But if you understand the rules of graphing, the things that we found here in this activity, right, you can interpret the graphs and therefore understand the motion. So, in number 1, for example, you saw something, I think, like this. Here's your position time graph, right? Here's your toy car starting near but not right at the motion detector. And if I get it going, you saw something like this happen. Okay, watch that again. You got a nice linear graph with a positive slope because it was moving away from the motion detector. It was moving to the right. Okay. And you might have drawn this on your sheet with a 0 y-intercept. If you did, that's perfectly fine. Technically, you couldn't really start the car at the motion detector because of the dead zone. Right? You were always starting at least like 20 centimeters away. So in reality, you probably had a bit of a y-intercept. Right? So let's kind of go with that here as we talk about things. Well, as we just discussed, the slope of this graph told us 2 things about the motion, right, of a position time graph. It told us how fast your object was moving, the speed of the object, but it also told you the direction it was moving, positive being to the right, negative being to the left, up, down, right, left. So speed is not a good enough term for that. Right? Speed just tells us how fast it's moving. We have another term that we use in physics, which up till this point, you may have used interchangeably with speed and not realized that you actually weren't using it correctly. Right? One of those terms that has gotten out into common English that actually has a little richer meaning when you're talking about it in physics. And that is the term velocity, denoted by a lowercase v. Hang on, there'll be a little bit extra to that. This is the slope of a graph of position versus time. This is the speed and the direction with which an object moves. Right? So velocity is a richer quantity. It is not enough to just say, hey, I'm driving 50 miles an hour in my car. That's its speed. Hence, speedometer that you look at on the dashboard. Right? If you say, hey, I'm going 50 miles an hour north, that's a velocity, right? That's a speed and a direction. Right? It's a more rich way to describe the motion of an object. And that direction can be north, south, east, west. It can have angles in it if we're getting 2 or 3 dimensional, right? Or it can be in 1 dimension as simple as positive and negative, right and left, right? Which is what we're going to be doing in this unit at least. Next few at least, we'll stick with 1 dimensions. Okay, so speed and velocity are related, but they are not the same thing. Speed is just how fast you're going. Velocity is how fast with a direction. Right? Velocity is the slope of a position time graph. Speed is the slope of a distance versus time graph. Our y-intercept, well, that was our starting position. We're going to call that x with a subscript of O, right? X sub O. This stands for your initial position. This is the y-intercept of the position time graph. Basically, it's your position at time 0. Right? The y-axis is when time is 0 on the graph. So it's your position at time 0. Now, why do they use an O or a 0 here? I don't know, really. I've heard several things, that it's an O for original, so this is your original position, or that it's an O that's really a 0, meaning your position at 0 time. I've often even heard this called x naught, right? And naught means nothing, right? So it's your initial, if you will. So there's a lot of different ways to say it, but this is the symbol that's traditionally used, okay? There are physics books and physics profs in simpler classes that will use an I for a subscript for initial. Kind of makes sense. But it's a little more traditional in more robust physics classes to use the O symbol here for initial. Right? So the slope of a position time graph is the velocity, the y-intercept is the initial position. Now, you might have noticed that we're now running into two different kinds of quantities this year. We have these new ones like position and velocity that have a size and a direction to them. Right? I mean, think about position. If I say something is 5 meters away, that's not really a full description. If I say it's 5 meters away north, well, now you know right where it is. Right? So having a position and a magnitude, a size, how far away it is, and a direction, right, is a complete description of something's position. Just like velocity is speed and a direction. Well, all physics quantities will basically fall into one of two categories. Quantities that have magnitudes and directions, and quantities that just have sizes to them. Quantities like position and velocity that have both are called vectors. And in fact, we're going to learn a whole branch of algebra this year called vector algebra. How do you deal with quantities that need to have directions associated with them? Okay. So a vector quantity has both a magnitude, that's a fancy way of saying a size, and a direction. Velocity, position. Right? To fully describe it, you need a direction as well as a size. Now, there is a way to tell in the notation, because some of you might have been saying to yourself, wait a minute, didn't we use little v for speed? And we did, right? We used little v for speed. The difference is going to be in the symbol. If your quantity is a vector, it is traditional to draw an arrow over your variable. Here's what I mean. Watch the screen. Watch here at the velocity. Watch here. Watch up here. Ready? Bam. See those arrows? Watch it again. Bam. Now they're vectors. Right? So you draw this arrow. If you're taking notes, highly suggest you go back, right, and put arrows on your V for velocity, your X's for position, or X sub O for initial position, right? Those are vector quantities. Haven't had to deal with that yet, right? Because when we were talking about things like circumference and diameter of circles, right, those are just sizes. Those are just magnitudes, right? But now we have these more complex quantities that include directions with them as well. Here, watch this little clip just for fun.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude.
Good physics.
Vector! That's me, as I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranha gun! Oh yes! Fires live piranhas. Never seen one before. Now you have my invention. You want a demonstration? Oh! Ah! It's so difficult sometimes to get all your rats.
Ah, yes. So, if a quantity is not a vector, which is most quantities you've dealt with in your life up to this point, then it's called a scalar. These are quantities that only have a size. Sometimes there are scalar parts to vectors, right? Speed is the scalar part of velocity. It's the size of the velocity, if you will. Some quantities are just scalars. Mass. It makes no sense to put a direction on a mass. This object has a mass of 5 kilograms south. What would that even mean? Right? So quantities like mass and circumference and diameter and speed and distance are all scalar quantities. Whether you know it or not, you've been learning scalar algebra all your life up to this point. Right? I'm going to teach you at least a little bit of vector algebra as we go throughout the year, where we're going to deal with quantities having both a magnitude and a direction. So you're going to see me be really specific in whether or not I put arrows on things. And ideally, you should be too. It's like an accent in, a foreign language. You don't put it on there, it changes things. All right, so you'll see this in my PowerPoints. You'll see this in my keys and in all those things. And it's a good habit if you want to write the language correctly, right, that you put an arrow on it if it's a vector quantity. And if it's not, you don't. Notice we think of time, at least in Newtonian mechanics that we're studying, as being kind of one directional thing, right? You don't go backwards in time, right? It only goes forwards. So we consider time a scalar, unless you get into more wacky physics. So, if we want to take this definition then of velocity as the slope of a graph of position versus time, we can put this into symbols. Why not? It's physics. Right, so if we take 2 points, of course, on our line, we find a slope by doing rise over run. The rise here would represent, well, we're graphing position on the vertical axis, so the rise would represent the change in the position. Right, this is the change in symbol, change in position. You find a change in by doing final minus initial. Right? X with nothing on it is final position. Right? So this is final position minus initial position. Again, some physics books will use an F and an I to show final and initial, but a little more traditional to use nothing and O or 0. Right? So final minus initial position. Notice that this quantity is itself a vector. See the arrow above it? Having a change in position 5 meters to your left puts you in a completely different place than if you have a change in your position of 5 meters to your right. So direction becomes important. And like many things in physics, we give these things special names. This is probably not a word you've heard all that often, like you have with velocity and speed, even though you may not have known that they were slightly different. But what we call the change in position in physics is displacement. So displacement is change in position. Final minus initial to find the change in. So if our rise is the displacement, our run would be the change in the time, of course, because we have time on the horizontal axis. So slope of this graph is the velocity. So slope is rise over run. So we can write this in symbols as velocity is displacement over time. Or if you want a little more mathematical way of saying it, it's the rate of change of position. This is how quickly your position is changing. Right? Like every second, my car is moving 20 centimeters. Right? 20 centimeters per second is your car's speed. If you're saying every second my car's moving 20 centimeters to the right, well, that's your velocity. Right? Or positive 20 meters per second or centimeters per second, or negative. Right? We can use all those different ways to show a direction. Yes, if you're already in calculus or you've had some calc, this is technically a derivative, right? But we don't have to get all calculus fancy in here because we can find slopes of straight lines with regular algebra and not calculus. If you want to see funkier functions, right, take APC next year and we'll do the calculus in there. Right? So this is kind of an equation, a math model for velocity, right? And this is what it means in words. And this is what it means as a picture, right? It's the slope of the position time graph. Multiple representations. Now, I want to talk a little bit about displacement and distance, okay? Because they're a little trickier than speed and velocity, right? Speed's just how fast you're going. Velocity is how fast and the direction. Right? But displacement and distance can be a little trickier than that, especially if we get into more than one dimension. So displacement, a vector, is kind of how far out of place an object is, right? How much has it changed its position? Whereas distance, a lowercase d for distance, right, is a scalar quantity. It's just a size, and it's how much ground the object's covered. How much ground it's covered, right, is distance. Let me show you where it gets a little tricky. Let me do a quick little example with you here. So let's say your physics teacher walks 4 meters east, 2 meters south, 4 meters west, and then 2 meters north. going to be a nice rectangle, right? I'm going to draw this out, and like in the video clip, I'm going to use arrows to represent these things, right? Because arrows have both a size, a magnitude, and a direction. So if we use the typical Cartesian coordinate system, where up is north, down is south, to the right is east, and to the left is west, right? 4 meters east would look like this. And then if we walk 2 meters south, right, we'd go 2 meters down, 4 meters west, 4 meters to the left, and then 2 meters north. Pretty okay with that? Right, that this diagram represents that sentence. We're going to do a lot more of that in another unit, okay? But, you know, in this unit, this is about as complex as things get. Well, let's compare distance and displacement. So what distance did I walk? I walked 4 meters, then 2 meters, then 4 meters, then 2 meters. So how much ground did I cover? 12 meters. Right? That's how far I walked. 4 plus 2 plus 4 plus 2 meters. But what was my displacement? My change in position, right, over this entire trip. I started here. Where did I end up? Hopefully you're saying, hey, wait a minute. Displacement would be 0 meters, right? Because I ended, right back where I started. So distance and displacement can be the same number, especially if you're like one-dimensional. If I walked 4 meters east and then another 2 meters east, my distance would be 6 meters, and my displacement would be 6 meters east, right? And my distance would be 6 meters. They'd be the same size, right? But you start getting into changing directions, and displacement can get a little bit wonky. Okay? You're going to get some practice in this, of course, in a wonderful little concept builder in the next few days. Okay? The difference between distance and displacement. You know, if I was in class with you, I'd probably tell you a little story where, you know, I know that you guys, teenagers, you like to sleep in on the weekends, right? So if your parents try to roust you out of bed this weekend, just look up at them and say to them, Mom, Dad, look, I learned in physics class that over the course of my entire day, my displacement will be, you're going to end up back in bed. So my displacement will be 0. So I might as well stay right where I am, because what's the point? Your parents will either, you know, start writing me mean emails about what I'm teaching you, or maybe if they're like engineer type people, they'll get all excited because you know some physics and, you know, buy you a car, I don't know, something, right? So the difference between distance and displacement, right? Now, since we have this wonderful linear graph, let's make a math model out of it. Why not? And since it's linear, we can use our old friend y equals mx plus b. Except we're not going to write a y, an m, an x, or b. We're going to use symbols that mean something. So instead of a y, we're going to use position. But notice, position, horizontally at least, like your cars were moving, is an x. So we're going to replace y with an x, with an arrow, because it's a vector. Have any of you noticed that I've spent a lot of time saying horizontal and vertical axis through the course of these videos? Right? I almost never say x and y axis like you would in math class. That's because I knew that very soon we were going to get to a point where we were going to be graphing x on the y-axis. And that can get darn confusing. Right? So I tend to refer to the axes as either horizontal or vertical, or what is your graphing? This is the time axis, this is the position axis. Right? So in this case, y is a horizontal position x with an arrow. M is the slope, but what did we just decide the slope of this graph was? Yeah, it's the velocity, which is a v with an arrow. X in this case is what we graphed on the horizontal axis, which is time, which is t. And our y-intercept is our position at 0 time, or our initial position, or x sub o. So here is a math model that describes this graph. But be a little careful here. This is a very specific motion because we got a linear position time graph. And what does that tell you? Well, linear graphs have what kind of slopes? Constant. And what does this slope represent? Velocity. And your cars, especially in this activity, were on this track, so they were moving in one dimension. So this is a math model for one-dimensional constant velocity motion. Hence the name of our unit, which is constant velocity, right? That's the model we're building in this unit. Things that move at constant velocity. We'll get to changing velocities a couple of units from now, right? But in this unit, we're going to focus on constant velocity motion. And in fact, one-dimensional constant velocity motion. So if your motion is changing direction, or it's changing speed, you're speeding up or slowing down, this equation doesn't work, right? You'd get a different kind of graph. And we'll look at some cases of that throughout the year. But for now, right, we'll stick to the one, but it helps to remember where it comes from to help to decide what model are we looking at. Right? We're looking at that of one-dimensional constant velocity motion. Oh, so this is really just a joke. Don't take notes on this page, okay? Just watch. So back before I had the equipment to do the moving right and moving left activity you did, I used to have students come up front and I would draw a graph on the board, and then I would ask them to walk the graph, which means I would ask them, okay, look at the graph and walk the motion that's represented by the graph. Okay? You're going to do some of this kind of thing with some concept builders, okay? But the very last one I would put on the board was this. Watch. Watch this graph again. This is a graph of position versus time. If you had volunteered to walk this graph back in those days, what would you have done? I'm going to give you 30 seconds to think about it. Back when I used to do this, I'd get usually a couple of different answers, because I'd usually have two people up there so that they could kind of talk to one another, help each other out. Sometimes I'd get people that would stand on the floor. So here's my floor, right? Here's my 0. They'd say, okay, I'm going to start to the right of 0, right? Because of this, because of the y-intercept. I'm going to walk out to the right, and then I'm going to walk back to the left. Because doesn't that kind of look like this? But remember, the graph is not the path. The graph is a representation of motion with its own rules that you have to follow. So often what would happen is they'd start getting these real funny looks on their face, and they, would be talking to one another. And if they did that for a little while, I'd say, what's the problem? And usually somebody would say, well, you can't do this. I would say, why not? They would say, well, let's pick a time. According to this graph, at this time, where am I supposed to be? I'm supposed to be in two places at the same time. This is a graph, but it's not a function. Remember the vertical line test in algebra? Right? It fails the vertical line test. Right? This is not a function. Just because I can graph it doesn't mean it's actually motion that exists in nature. Right? So this was kind of my little trick to see if they would, just do what it looks like, especially when they see it drawn on the board like this, right? Or whether they would actually interpret the graph. So one year, some smart kid in class said, well, the only way this would work is if you could do this. Watch this. Yes. For those of you that, like me, like your Star Trek, right? That's the transporter sound, right? So we have somebody split in two people. They're at two different places. Notice one is to the right of 0, and one is even further to the right of 0. And then as time goes on, they become one person somewhere out here. Yeah, it's not real Newtonian mechanics, folks. Hope you've enjoyed this long and sometimes weird discussion of one-dimensional constant velocity motion.